Hi, so in our last video lecture, we derived the dynamic equation that would allow us to solve for both temperature as a function of both distance and time for heated fluid flow through a pipe when there's a constant surface flux applied. So we came up with this dynamic equation to give us the change in temperature with time for an individual node I. Then we can do this for all nodes of our system, and we can solve this in Python and demonstrate how the temperature profile evolves over time. We also took the time to derive a steady state version of this equation, which we have here. So now we're going to take the time to go ahead and code this energy balance into Python. So I'm using the Python Spider IDE and Python version 3.7 to do this. So first we're going to start off by importing some tools that we're going to need later. So we're going to use this tool NumPy, which will have some certain mathematical functions that we'll need. And we're going to import a plotting library, Matlab. So we're going to use those later because we'll need those tools. So first we're going to define the length of our pipe. Let's just go with L equals 50. And it's always nice to put in units. So everything after the pound sign are just going to be comments. Let's define the radius of our pipe as 0.1, which is also going to be in meters. And we're going to want to break this into spatial nodes. So if you watched the previous video, we took this pipe and we did an energy balance for an arbitrary node. Now if we want this finite difference approximation of our system to approach a continuous system, we're going to want to use a lot of nodes. So I'm going to use 100 nodes, but we're going to set up the code so that you can use different numbers of codes just by changing this one number. So this is going to be number of nodes used. Okay. Let's define a mass flow rate of 3, and I'm just going to use kilograms per second. Let's define a heat capacity, just assuming this is water, that would be 4180 joules per kilogram per Kelvin. So that is the heat capacity of our fluid, which is water. We're also going to need our fluid density, which I'm going to call rho, and that we're just going to round this off to 1,000 kilograms per cubic meter. And that is the density of water. And finally, we'll just define the number pi, because we'll need that. So let's assume that the inlet temperature of our water is 400. So the water's coming into our pipe at 400 Kelvin. So this inlet temperature, so we just have this constant supply of 400 Kelvin water. We're also going to have to define an initial condition. So what temperature is the water before you start heating it and flowing this hotter fluid inside. So I'm going to define our initial condition, T0, as 300. And this is just a scalar right now, but we're going to turn that into a vector so that it represents the entire length of the pipe. So that's the pipe fluid initial temperature. Okay, so let's first, we need to define our flux term. So I'm just going to use this Q underscore flux, and this is going to be 100,000, and the units there would be watts per meter squared. So this is the heat flux into the fluid. And we're going to simulate this out to a final time of 700, and this is going to be in seconds. We're going to start at time t equals 0 and simulate it out. So just to kind of break up these different sections and make this a little bit easier to read, I'm going to add some spaces in there. So we're going to take time steps of 1 second as we do this numerical integration. And because we have a 50-meter long pipe and 100 nodes, my delta x, which I'm just going to call dx here, is going to be L over n. This is going to be in meters, and this is our node thickness or our node width. Okay, so for convenience later, I'm going to define this x vector. So this is just something that'll allow us to track our temperatures based on location. So we're going to do np.linspace, and we're going to go from dx over 2 to L minus dx over 2. No, yeah. So our first node is going to be at dx over 2. We're just going to put a point. Basically what that's doing is it's going to, if setting up linspace, we're going to define x as being in the middle of each of these nodes. So that dx over 2 is going to be our first node right there. So this x just puts a number representing the exact midpoint of each individual node. Okay. So our initial temperature is going to be, we're just going to say this is going to be 1s, and this is going to be n elements long, and we're going to multiply that by our initial temperature. So what that does is it creates a vector that's going to be this n, it's going to be 100 elements long, and we're just going to populate every one of those elements first with 1s, but then when we multiply that by our initial temperature, that's going to give us a 100 by 1 vector where every element is 300. Then we're going to initialize our temperature derivative, and we're just going to say that this is just equal to zeros, also of length n. Okay, we're going to set a vector, well, we're going to predetermine our time steps. So this is going to be np.arange, starting at 0, going up to our final time that we defined previously, and taking steps of dt. Okay, so now all we need to do, we need to go in and actually type out this dynamic energy balance equation that we derived previously. So first we're going to start by taking j time steps. So we're going to take time steps up to the length of this whole vector. So we're going to say for j in range, and we're going to go from 1 up to the length of this t vector. So at each time step, these are the things that we're going to do. We need to calculate our temperature derivative for every element. So you could do this in a for loop. I'm just going to actually do this as vector math. So our dt, we're going to start with element 1, and we're going to go out to element n. So the way that Python works, Python actually starts counting at 0. So our very first node here is actually going to be represented in Python as our 0th node. Then we're going to start here. So this vector starts by defining with node 1, and it goes out to node n. But we're going to have to define this 0th node differently because it gets the inlet temperature directly and does not get an inlet temperature, does not have an incoming temperature from a previous node. It's just getting it directly from the source. We have to code that one a little bit differently. So we're going to refer to our energy balance equation here that we just derived. So if you watched the previous video, you know where this came from. So the change in temperature of node I is equal to this constant flux plus this flow term where it receives energy from the previous node and loses energy based on its own temperature. So this is the equation we're going to code in here, but we're going to do this with vector math, so we capture all of these, every node at the same time. So this is going to be equal to our mass flow rate times our heat capacity multiplied by, and now we're going to use this vector math, so the change in temperature of node 1 depends on the temperature of node 0 coming in. So we're going to go here from 0 to n minus 1. So that represents our inlet temperature. And then here we're going to go from T 1 to n. So we're losing energy from each node by the temperature of that exact node. So notice that our out terms, our advective out terms, have the same indexing 1 to n as our derivative term, 1 to n. Okay, and then we also have our flux term coming in. So we have this plus q underscore flux multiplied by the area over which that flux is applied. That's 2 times pi times r times dx. And then we've got this whole guy needs to be divided by that denominator, and that is going to be rho times cp times dx times pi times r squared. Okay, so that will basically be the energy balance for every node except for the first node. So for the first node, which is actually in Python going to be node 0, we'll have almost the same equation, except we'll go node 0. The inlet flow, instead of being something that comes from the previous node, this is going to be Ti, and then it's going to lose energy proportional to its own temperature, and then everything else there should be the same. So now we've defined our entire dt vector going from node 0 all the way up to node n. So then we come here, and actually I do want to point out that Python does not include, so our vector length is n units long, but 0 is one of those. So that means our last element is node n minus 1, or node 99 in this case. So in Python, when we define this range, this would actually include node 1 up to node 99. Then once you add in node 0, that gives us our full 100. So now we've calculated the derivative of temperature with respect to time at a particular instant in time. So now we need to do this Euler integration. So that is going to be, our temperature is going to be equal to our previous temperature plus our derivative of temperature with time that we just defined, multiplied by our time difference. Okay, so now if we hit go, this code is going to loop. It's going to take these small steps in time. At each step in time, it's going to calculate this complete vector representing the change in temperature with time of every node. After it calculates the change in temperature with time, we're going to do this approximation that our new temperature is equal to our old temperature plus our derivative vector times this delta t. So we can do all this, and it's going to simulate, hopefully, but we're not going to be able to see anything, so we need to add in some plot functions here. So these plot functions, we're going to do, first we need to initialize our plot. Then we are going to actually plot it out. Okay, so we use these commands to plot our temperature profile. So our temperature we've just called T. So we want to plot X on the X-axis. Then we want to plot T, and let's go ahead and assign this a color. And you'll see why we're doing this here in a minute. So let's make that blue, and let's give it a label. This is going to be our transient temperature profile. Okay. So let's label everything. So our X label, we're going to give that distance in meters. And our Y label is going to be temperature in Kelvin. Let's give it a legend. And let's put that legend in the upper left. Finally, we need these commands to actually show the plot. And as Python goes through and steps through, it's working at computer speed, so it happens really fast. So if we want this to actually go slow enough for us to be able to see each little snapshot, we're going to give this a pause command. We're going to have it freeze on each frame of this little video that we'll show for 5/100ths of a second. So another little trick that I'm going to do here in the top of our loop is I'm going to have this pop up the figure, and then I'm going to have it clear everything so we don't get, so what this is going to do is going to plot, at every time step it's going to plot a new line. So we want to go clear out the old lines so we don't just have a bunch of lines accumulating on here. So if we've done everything correctly, we should be able to hit go, and this should run our code and pop up this plot. So you can see, so we have that fluid coming in from the left, so that's starting to heat things up. But you'll notice our fluid itself, and I need to go back and actually lock in our axes so you can see relatively how this is happening. Let's go ahead and kill this for now. Alright, so one thing I'm going to do, and one thing that I missed before, was to give this a fixed axis. So plt dot axis, and we want to have this go from 0 to L in terms of distance, and then have it go from 298 up to 750, and I just know this from solving this problem previously. Okay, let's give that another try and see how we look. Oh, still got our old one going. I didn't successfully kill it. Okay, so now we've successfully killed it. Alright, let's see how our plot looks. Alright, so we got temperature on the y-axis. You can see, so we have that fluid coming in, and as it starts to work its way from left to right, you definitely see this front coming here where that fluid temperature starts to rise. However, the rest of the pipe, even though that hot fluid hasn't hit it yet, notice how its temperature is rising as well, and that's due to that constant flux being applied. So you see that the temperature everywhere is rising. It just happens to rise more quickly here at the front as that new hotter fluid starts working its way all the way down through the pipe. And if you recall, our steady state temperature that we derived previously is just, it's this inlet temperature. This is our intercept. Then it's going to have this constant slope. So everything is in here is a constant except for x. So we're going to expect this to just be a straight line where the y-intercept is our inlet temperature. And you can see that that is the case here with our inlet temperature being equal to 400 Kelvin. Okay, and you can see once we get close to steady state, you can see our steady state temperature profile is in fact a straight line. However, doing this fairly simple dynamic solution, we actually get to see how that temperature profile evolves over time. So applying this same methodology, you can solve a wide range of very complex problems just by something simple as doing a dynamic energy balance like we've done. So let's double check our work. So what I'm going to do, because we already know, we've already solved for the steady state temperature, I'm going to create a new variable called TSS, and I'm just going to enter in this equation, which is our steady state temperature profile. And we can see how that looks up against our dynamic temperature profile. So that is going to be our inlet temperature plus Q flux multiplied by 2 times pi, 2 times pi times r times x. And notice we initialize this entire vector of x's before, so this is going to also be a vector that's the same length, divided by m times Cp. So now we can add this line to our plot by just inserting another plot command, only this time we want to plot TSS, and let's make this one red, and let's give it the label steady state. All right, so now when we plot, we'll be able to see our dynamic temperature profile evolving, and we'll have superimposed on top of that our steady state temperature profile. So we can see how this dynamic temperature profile compares to the real solution. So one thing to keep in mind is that for the dynamic system, we made an approximation. We discretized this actual pipe into a bunch of smaller nodes, whereas the steady state solution is based on the real continuous system. So we'll see how well our spatial discretization does. If it's not very accurate, we might want to add more nodes to make this a better approximation of the real solution. Okay, and as you can see, we've got our steady state temperature profile plotted there in red, and as you can see, as our dynamic system heats up, you can see it's lying basically right on top of our steady state. So that tells us that this is a pretty good numerical approximation of our problem. However, in solving for the dynamics of the problem, we get all this extra information, and we can basically create a whole video of how this thing evolves. So again, you see at the end of the pipe, the hot flow front hasn't reached this yet, but it's still heating up because of that constant applied flux. So hopefully at the end of this, we see these two lines are perfectly coinciding, or very close at least. Okay, so this is a nice way to confirm that the work we've done is correct. So we can, now that we have this dynamic simulation, you can try a bunch of different scenarios. You could have different initial conditions. You could actually simulate the system to handle changes in either the applied flux or in the flow rate or in the inlet temperature, and you can have a really nice and accurate simulation showing how that temperature throughout your pipe is going to evolve even when kind of non-standard or weird things start happening to it.